Welcome back. Now I would like to talk about parametric models in least squares and linear regression. All right. First of all, the relationship between a dependent variable y, you can think of this, and independent variable x, you can think of this. In the previous lectures, we mentioned this can be the time and this can be the function that depends on time. All right, so basically this relationship has a specific form. Right, in the previous lectures, we used the line that fits basically to the data that was looking like it is coming from a line equation. In this current lecture, basically, we would like to generalize it to parametric models. Maybe it is hard to guess at the beginning, but if you look at this data, this looks like it is coming from some constant plus w1x, w2x to the power of 2, w3x to the power of 3. I'm going to run a simulation. Basically, this, at least it should be clear like this is looking like a polynomial. So you can start with, for example, line. If it doesn't fit, right? If you only use this part of the equation and without this, you are going to get a fit looking like this. Then you can try these three without this term. It won't fit perfectly. And once you include this term, you are going to see that it fits perfectly. And again, I am going to illustrate this in a MATLAB example in this video. So nevertheless, so let's say initially we guessed like this is a polynomial model which fits into this equation. And again, these guesses, initial guesses comes more naturally once you have experience with least squares and linear regression. So bear with me. So I would like to write this in vector format, basically theta containing the basis, basically this, the bias that multiplies W0 and x to the power of 2 and x3 that multiplies W1, W2 and W3. I put these initially unknown terms inside this vector. And basically for this is just an example, and I am going to generalize this momentarily. So we are going to do linear regression and least squares to find the analytical as well as the iterative gradient descent solution for W. I would like to say a few things about parametric models. Depending on the chosen model, parametric models can be less flexible than the non-parametric models. I should have mentioned that. Right, because it assumes a certain form. And if your data is in that certain form, great, then you should move with the non-parametric models that I am going to cover in the next two videos. Another point that I would like to make, parametric models often require less data to estimate W as compared with the non-parametric models. This is great if you are if you are sure that you are dealing with a parametric model. All right, in this video we are. In general, right, if you look at this theta, this is basically 4/1 because we choose this basis to contain these functions, and hence unknown parameters become also 4/1. In general, basically you can include anything inside theta and there will be a corresponding W, unknown weights. So I am going to call the dimension of this theta to be S. In the previous example, it was 4, and unknown parameters S as well. And if you watch the least squares video, very similar to that one, we would like to find W that minimizes this cost function. It is the same cost function from the previous videos, just the content of the basis function is different. Basically, you are going to, with some steps, you can represent the first line like this. Basically, if you expand this for I equals to 1, 2, 3, same for y, to all the way up to n data points that you have, then you are going to construct this omega matrix, which will be S by N. Again, at the end of this video, you are going to see a MATLAB example that I did this precisely. This is multiplied by W, and this stores the first data point y1, y2, yn. To refresh our minds, let's look at this data. For example, right, this contains n number of data. This specific data is xi, whatever the value is, and it corresponds to a yi. And this is the first data, y1, that corresponds to x1 here. So that's the notation that we use in here. Anyway, and this second line can be representing with this norm, Euclidean norm. Let's remember, Euclidean norm of, for example, a vector is Xc transpose Xc. Actually, it is this if you don't have this to the power of 2. Since you have to the power of 2, this square root disappears. You just have Xc transpose Xc. Just a notational convenience. If you don't believe me, you can verify this corresponds to this corresponds to this. This is just how we group things. And we did this grouping in the previous video on least square more precisely. Since we are using more or less the same approach, you can take my word for it that we have this equals to this. It is basically the same cost function, and least squares problem deals with finding the minimum of that cost function. And minimum occurs at critical points such that gradient of v, which is the scalar valued function's partial derivative with respect to vector w, it needs to be equals to 0. So when the gradient of this cost function equals to 0, we find the minimum points. All right, so how can we calculate dv? Basically, I mentioned before this equation coming from matrix cookbook. That I mentioned in the first videos. Let me make sure the naming is right. Matrix cookbook, yes, that was the reference that I gave in the introduction video for this regression and control series. So for a given vector b and z and matrix A, if you take its partial derivative with respect to dz, that's the answer that is coming from that great resource, Matrix Cookbook. So in our case, our dv, basically we are going to find dv by taking the I forgot to include here, partial derivative of this with respect to dw, which is equals to, let me include this here. We are going to take partial derivative of this function. And if you expand this based on the Euclidean norm, as I mentioned, if you think inside as the Xc, this is Xc transpose multiplied by Xc. Now at this point, to take partial derivative of this cost function with respect to dv, this is exactly in this format. So basically using this Matrix Cookbook reference, you are going to have this gradient of this cost function v. And we can solve this, we can find a solution using basically least squares analytical solution as well as the iterative solution using gradient descent. First, I would like to talk about the analytical solution. I set dv gradient equals to 0. And in this case, this or this becomes 0. I can divide both sides by 1 over n, so you can get rid of this. If you do that, you have 0 equals to omega y minus omega transpose v. And if you solve this v, you are going to get v equals to omega transpose inverse omega multiplied by y. And when s greater than n greater than s, then this is generally non-singular such that inverse exists. Because remember, omega is an S by n matrix, And if n greater than s, so s by n matrix, and here n is greater than s, multiplied by, this is omega, multiplied by its transpose, omega transpose, basically n by s, then it will create an s by s matrix. And since you are multiplying a fat matrix by its transpose, it will be generally non-singular, so that inversion exists. And here you go, this is the analytical solution that you can find for parametric models. Now, how you use gradient descent type of a solution to least squares. If you remember, basically from the gradient descent video, I posted a video about gradient descent. You can watch to learn more in details. And also in that gradient descent video, I am discussing, why should we prefer a gradient descent and iterative solution since we already have an analytical solution. And briefly I can mention, because gradient descent or iterative or online solution is robust to new data, changes in data, and also it has a lot of connections to control theory that I will reveal in the upcoming videos. Again, I discussed this in the gradient in the video on this lecture series called the gradient descent. I am right now diving directly to the solution. Basically, if you remember, in the gradient descent, we basically update the next parameter for w using its current value minus a gain parameter alpha multiplied by the gradient. So because we are going in a negative direction to the gradient, it is called gradient descent. I gave more examples and more intuition about the gradient descent approach, a very popular machine learning approach. In the gradient descent video, in order not to be repetitive, I am not covering in here. So basically, I am inserting the gradient here, and you obtain this. Then I am grouping terms that depending on w and that doesn't depend on w. Basically, this A matrix is given here and B matrix is given here. So basically, to find gradient descent solution to this least squares minimization problem, you need to implement this discrete time difference equation, and k changes from 0, 1, 2, 3, ... Basically, it shows how we update, how we find the next value of v using the previous value and the gradient. And as you may remember from the former videos on this lecture series, A will be S by S matrix. Previously, it was, for the line problem, it was 2 by 2, if you remember. It will have S eigenvalues, and alpha needs to be chosen such that A matrix is sure, meaning that the eigenvalues of A needs to stay in the unit circle of the complex plane. This is the complex number. Let me write it like this. This is the imaginary value axis, real axis. This is the unit circle, 1 minus 1, j minus j. Eigenvalues of A must be contained on this unit circle. And this unit circle, I give a reference in the gradient descent video, as well as gradient descent with momentum videos. Basically, it is coming from analyzing the convergence, under what conditions these discrete time difference equations can converge. So it has connections to control theory. And when A is sure, then this gradient descent solution is guaranteed to converge to the actual analytical solution as k going to infinity. All right. We found analytical and gradient descent solution to this parametric model. So let's run some MATLAB examples. I am considering 50 number of data points, and using the linspace command, I am just generating numbers for x 50 times between the interval minus 5 to 5. This is x is the independent variable. And here is the, y equation, basically in this case. In general, this y is unknown, right? If it is known, why should we gradient descent? And I wrote it like this just for the sake of this video, just to generate some data points, and I will pretend that the structure is unknown. I will first start with a linear fit, okay? And in this case, I am choosing omega to be, I am putting ones, basically. That corresponds to W0, and this corresponds to W1, and this is linear. This corresponds to literally this model, 1 multiplied by W0, x multiplied W1. And I put all the x points here, the data that is collected, and I am running the analytical solution, inverse of omega omega transpose omega y. And after I find the analytical solution, basically this is for plotting purposes, I am running x, I call it xp, okay, from 5 to minus 5, and y hat is the estimate. Here I am using the w points, w transpose multiplied by 1x, and then these for data recording and these for plotting purposes. You can always pause this video if you want to code it by yourself, but here is the solution. I am trying to fit a linear model, and this is the best linear least squares fit, and of course it doesn't fit the data because the data points are not, they don't represent a line model. Now I am basically in addition to x, I am adding x to the power of 2 here and here. These are the changes in the code, okay, only 2 changes. And so our model changes to y hat equals to w0 plus x w1 x to the power of 2 w2. I am increasing the order. And when I do the fit, I am getting w0, w1, and w2 values. Now it won't fit, so I need to increase the order of the basis theta function even further. All right, so now I am adding x to the power of 3 term. Now we should match because this was the actual model. And these are the changes in the code, So basically I added one more term here. Now this is a great fit. You see here, maybe you realize there is some noise, right? Random. I added some randomness to these data points. Otherwise they will all appear exactly like this. So these are the estimated W, the analytical solution. Comparing this with this is kind of a little bit off. Minus 1.5, minus 1.54, this is accurate, and these other two are accurate. And these are slightly off, especially the first one, due to the noise, and this is something to basically, I'm just make you to understand the underlying some principles, and I would like to talk a little bit about noise. First of all, this is a great fit, and you can use this estimation confidently. However, I would like to discuss one point. If the noise is decreased, now I am going to decrease the noise from, it was, the multiplier was 2.5, right now 0.5. It is, again, a great fit, and you see that data red points are more on the black line because there is no randomness, we reduce the noise. And you see that not only these 3 parameters, but also the first one is very similar to 0.5. This is so W stays close to W, the analytical solution stays close to the actual values when you have less noise. If you have more noise, you will still have a great fit. Like in here, I added a good level of randomness. And you can quote this video, you can increase this to 5, 7.5, even 10. You are going to get again a great fit because of the power of the least squares. Basically, least squares tries to minimize all these errors between the curve and the data, like these distances here and there, up to a minimum. So you are going to get a still great fit. All right, so I would like to find the solution using gradient descent approach as well. And this is the same part of the code, generating xy points, same omega for this final case. I am choosing alpha to be 0.0007. This is motivated by the fact that I try to maximize the alpha, and this is the maximum value. In this case, the eigenvalues of the A matrix are at the unit circle. If I increase this from 0.0007 to more, then one of the eigenvalue will go outside. I believe this one was becoming more than 1. It is not desired. So I need to implement things theoretically correct rather than trial by error. So, and you should do like this. And then I am running this iteratively to find W starting from the 0 initial condition. I am doing 8,000 steps, and then I am plotting figure 1 and then evaluating how this fits to the data. Again, you can stop the video and take a look at this code it yourself. I am going to show the results. These are the W estimates. This is W1, W2 estimate, W3, and W4. You can stop it honestly around 5,000 iterations, even 3,000 iterations, and I encourage you to do that. You are still going to have more or less a great fit. And this is the plot when I use W1, W2, W3, W4 values after the end of the iteration, or I am using this W1, W2, W2 points after on the 8,000 iteration. It is a great fit. I think this video served its purpose in terms of how you generalize line equation that we covered in the previous videos to any parametric model. I am not going to do a gradient descent with momentum example here because we don't have any oscillation issue. They converge pretty nice. Please watch gradient descent with momentum. I highlighted the importance of adding a momentum term when it is needed. It is just not the purpose of this video. And if you like the video, basically subscribe, turn notifications on, and send a like, and see you in the next videos.